In this chapter, we're going to explore exponentiation. Exponentiation involves multiplying the same number many times, just as multiplication is adding the same number many times. The superscript tells us how many times to multiply the number. For example, when the exponent is 3, we're multiplying the base 3 times. This operation is called 2 to the power of 3, or 2 to the third power. 2 is the base and 3 is the power. We will first explore the properties of exponentiation, then study logarithms, which are the inverse of exponentiation. If the exponent is 1, then the output is just a base. More precisely, x to the first power equals x. For example, 5 to the first power equals 5. Negative 2 to the first power equals negative 2. And x plus 2 to the first power equals x plus 2. If the exponent is 2, then the output is the base multiplied by itself, or base squared. More precisely, x squared equals x times x. Similarly, if the exponent is 3, then the output is the base multiplied 3 times, or base cubed. X cubed equals x times x times x. Let's try writing x cubed in terms of x squared. We can substitute x times x with x squared as follows. Since 3 equals 2 plus 1, we can write x to the 2 plus 1 equals x squared times x. When we add 1 to the exponent, we need to multiply another x. Then for some exponent m, x to the m plus 1 equals x to the m times x. Here are some examples. 5 to the 2 plus 1 equals 5 to the 2 times 5, and 3 to the 4 plus 1 equals 3 to the 4th times 3. This is a recursive definition, which just means that the exponentiation is defined in terms of another exponentiation. Let's use this definition to calculate 3 cubed. 3 cubed is equal to 3 to the 2 plus 1, which is equal to 3 squared times 3, which is equal to 3 to the 1 plus 1 times 3. And this is equal to 3 to the first times 3 times 3. 3 to the first is 3, so this is equal to 3 times 3 times 3, which is 27. Next, let's replace 1 with n as follows. X to the m plus n. When we add n to the exponent, we need to multiply by x n more times. For example, 4 to the 2 plus 3 is equal to 4 times 4 times 4 times 4 times 4, which is 4 squared times 4 cubed. Also, 4 to the 2 plus 3 is equal to 4 to the 5th, which is 4 times 4 times 4 times 4 times 4. 4 squared consists of 2 4s, and 4 cubed consists of 3 4s. 4 to the 2 plus 3, or 4 to the 5th, consists of 5 4s. Thus, adding a number to the exponent is the same as multiplying by the base raised to that number. More precisely, x to the m plus n is equal to x to the m times x to the n. In other words, x to the power of m plus n is equal to multiplying x, m plus n times. X to the m multiplies x m times, and x to the n multiplies x n times. So x to the m times x to the n also multiplies x m plus n times. Here are some examples. 5 to the 2 plus 6 is equal to 5 squared times 5 to the 6th. 2 to the 3 plus 4th power is equal to 2 to the 3rd times 2 to the 4th. When we increase the exponent by n, we multiply by the base n more times. Inversely, when we decrease the exponent by n, we multiply by the base n less times. For example, recall that x cubed equals x times x times x. and x to the 3 plus 2 is equal to x times x times x times x times x. We multiply by x 2 more times. In contrast, x to the 3 minus 2 equals x. We multiplied by x 2 less times. In other words, we removed x twice from x times x times x. This is equivalent to dividing by x twice. Next, let's calculate x to the 3 minus 3. We start with x cubed, which is x times x times x. Then we divide by x 3 times. The result is 1. Thus, x to the 0 equals 1. Here are some examples. 5 to the 0 equals 1, negative 10 to the 0 equals 1, and y plus 7 to the 0 equals 1. What if the exponent was negative? We can write a negative exponent as a subtraction from 0. For example, x to the negative 1 equals x to the 0 minus 1. We begin with x to the 0 and divide this by x. Since x to the 0 equals 1, x to the negative 1 equals 1 divided by x. Similarly, x to the negative 2 equals 1 divided by x, which is equal to 1 divided by x times x, which is equal to 1 divided by x squared. And x to the negative 3 equals x to the negative 2 divided by x, which is 1 divided by x squared divided by x. This is equal to 1 divided by x cubed. In general, x to the negative 1 times y is equal to 1 divided by x to the y. Let's try to prove this more precisely. Recall that x to the m plus n is equal to x to the m times x to the n. Now suppose that n is equal to negative 1 times m. Then x to the m plus n is equal to x to the m minus m, which is x to the 0, which is 1. Then x to the m times x to the n equals 1. If we divide both sides by x to the m, we get x to the n equals 1 divided by x to the m. Since n is equal to negative 1 times m, x to the negative 1 times m is equal to x divided by x to the m. Let's look at some examples. Consider the expression 3 to the 2 minus 2. 3 squared equals 9. When we subtract by 2, we divide by the base 3 2 times. Then 3 to the 2 minus 2 is equal to 9 divided by 3, which is 1. Alternatively, since 2 minus 2 is equal to 0, 3 to the 2 minus 2 is equal to 3 to the 0, which is 1. Note that 3 to the 2 minus 2 is equal to 3 squared times 3 to the negative 2. Since 3 squared equals 9 and 3 to the 2 minus 2 equals 1, we claim that 9 times 3 to the negative 2 equals 1. Then 3 to the negative 2 equals 1 over 9. Recall that 3 to the negative 2 equals 1 divided by 3 squared, which is also 1 divided by 9. Here are some other examples. 4 to the negative 2 equals 1 divided by 4 squared, which is 1 divided by 16. 2 to the negative 3 equals 1 divided by 2 cubed, which is 1 over 8. And 5 to the negative 4 equals 1 divided by 5 to the 4th, which is 1 divided by 625. Let's see what happens when we raise 0 to a power. As with other numbers, when the exponent is a natural number, we multiply by 0 many times. Here are some examples. 0 cubed equals 0 times 0 times 0, which is 0. And 0 to the 5th equals 0 times 0 times 0 times 0 times 0, which is also 0. Notably, the product of many zeros is still 0. Thus, if x is greater than 0, then 0 to the x equals 0. What if the exponent is also 0? X to the 0 equals 1, so isn't 0 to the 0 also 1? Surprisingly, people disagree on this question. Previously, we calculated x to the 0 by starting with x to the 1 and dividing by x. Then 0 to the 0 equals 0 to the first divided by 0. But 0 divided by 0 is undefined, so we could reasonably argue that 0 to the 0 is also undefined. Finally, let's suppose that the exponent is negative. Recall that x to the negative 1 times y is equal to 1 divided by x to the y. Then 0 to the negative 1 times y is equal to 1 divided by 0 to the y. If y is a positive number, then 0 to the y equals 0. Thus, we claim that 1 divided by 0 to the y is equal to 1 divided by 0. And 1 divided by 0 is undefined. We can reach the same conclusion when y is negative. Thus, when the exponent is negative, the operation is undefined. Consider the expression x to the m to the n. X to the m multiplies x m times, and x to the m to the n multiplies x to the m n times. Thus, x to the m to the n multiplies x m times n times. X to the m times n also multiplies x m times n times. Thus, x to the m to the n is equal to x to the m times n. Here are some examples. 2 to the third to the fourth is equal to 2 to the 3 times 4, which is 2 to the 12th. A plus 3 to the 6 to the 9th is equal to a plus 3 to the 6 times 9, which is equal to a plus 3 to the 54th power. If the base is a product, we can distribute the exponent to the terms of the base. For example, 4 times 5 to the third power is equal to 4 times 5 times 4 times 5 times 4 times 5. We can rearrange this expression to 4 times 4 times 4 times 5 times 5 times 5. This is equal to 4 to the third times 5 to the third. Thus, we can conclude that 4 times 5 to the third power is equal to 4 to the third power times 5 to the third power. In general, x times y to the nth power is equal to x to the nth times y to the nth. Here are some examples. 2 times 3 to the fourth power is equal to 2 to the fourth times 3 to the fourth. And x plus 1 times 5 to the seventh power is equal to x plus 1 to the seventh power times 5 to the seventh power.